Okay, so let's do this. We will do birational geometry today. So let me recap what we have so far. So this is a very short summary of the objects, of the things that we have seen in this mini course. So there you have. So think about a W surface. So a surface W, which is a normal projected surface with only Wahl singularities. Wahl singularities are these cyclic quotient singularities here, and you have many. Okay, that is the surface. And now put this surface in a family. So W is the central fiber, and then you have the WD, which is smooth. This is the threefold that has canonical class Q Cartier, and this is what I call Q Gorenstein smoothing. Okay, this is going to be the object today, and I will do birational geometry on this object. Now, the way we construct this kind of thing is almost always abstract, like this example. This is an example that I showed you yesterday. So starting with an elliptic fibration, you have this configuration of rational curves. You see three singular fibers and these two sections. You do a blow up like this. You find these wall chains that you contract. Then you have the W. Then there is a way to prove, I don't know if you remember, but on Tuesday I told you a way to prove that there is no obstruction in a case like this. And so from this no obstruction, you can find a situation like that for this W. And this is the way we construct examples. Okay, so, but in principle, you just think of in this way. We have a W and a smoothing. Okay, and this is going to be my object today. But I will start with birational geometry, the classical one, so scuola italiana. And this means X non-singular projected surface. And here you have the canonical class, K of X, which is going to control the birational geometry. So this is the canonical class. And by the way, I might be using, again, some invariants. Like you see there, you see a PG, a Q. So let me recall that. PG is going to be the dimension of the sections of the two holomorphic forms on X, which is also H2 of OX. And Q, in this case, is the dimension of the one form, which is also H1 of OX. And we have also this fundamental invariant K squared, which you can think about it as the first Chern class of this X squared, so this number, which is an integer. And you have the Euler characteristic, the topological one, of X. Maybe I also mentioned the Euler characteristic of X, which is 1 minus Q. Classically, Q is called irregularity of the surface, and this is the geometric genus. Okay, all of this classical. And now how you run MMP, or how you do birational geometry with this K, with this X. So you ask to X if Kx is nef or not. So remember that Kx nef if for every curve that you have in X, you have that the intersection of the curve with K is positive or 0. So it happens that K of X is nef, then we call X a minimal model, and then we classify that. I will show you. I will recall how to do that. But if it's not, if K of X is not nef, then there exists, you can prove that there exists a gamma minus, which is a P1 inside of X, so that gamma minus dot K of X is negative. And then you have three options. So now you ask, well, what is the self-intersection of this gamma minus? So I go here. if gamma minus square is negative also, then something happens. Gamma minus. So say that there is nothing like this, then gamma minus square could be 0, or gamma minus square is positive. Then in this case, when you have this situation, this gamma minus is a -1 curve. That means that gamma minus square is -1. And by Castelnuovo, scuola italiana, you have that this x is a blow-up at one point of some other non-singular projective surface, x prime, and you have a situation like this. And now you ask to x prime the same question, and you keep going. So if the canonical class here is negative, it's not Neff, then you either go here, here, but if you have a situation like this, then you keep going. This is like a machine, not Neff. But if it's Neff, then we have that x is minimal model. So among all the surfaces that are birational to x, you are choosing one, and this is unique. And then you try to classify this x, and you use this collider dimension for that. And then you have if the collider dimension is 0 or 1 or 2, then you put names here. So if it's 0, then you can prove that you have a K3 elliptic, no, abelian surface, or the tal quotients of this. So from the K3, you can go to the Enriquez, and from abelian, you can go to the bielliptic. If you have collider dimension 1, then you have an elliptic fibration on x. So it's something like this, x over some curve. And the general fiber is going to be elliptic, like this. So there is this structure. And here you put the name general type, which is a complete mess. It's a total mess. Difficult to understand. But in this case, you want to talk about, in this case, you have that the canonical class is also big. So big in Neff, and you want to find a canonical model where the canonical class is ample. And so you go from this x to x can, and this process is unique. And you contract this is a birational map that contracts exactly ADE. Let me put it here. ADE is joint configurations. So x can has only Duval ADE singularities. And canonical class of x can is ample. And you start to think from here about the moduli space of such surfaces. This is difficult, very, very hard to think about these general type surfaces. So in this case, when there is no such a curve, and now you are here, then you have that x is a rule surface, a minimal. So it's a fibration of spheres over a curve. And so this is birational to P1 times the curve. So all the fibers here are spheres. Here you might have degenerations of these elliptic fibers. And here, if you are in the situation, so if you're not here, you're here, then x is P2. Okay? So this is classical. I bet you know, everyone knows about this. So now in my talk, I want to do this, exactly that, but for those degenerations. And today, I will talk about exactly this part, which is much more complicated. Exactly this part, what to do here when you find a curve like this. And also, I want to finish the talk talking about the minimal models a little bit. So also this part, more or less. And tomorrow, I would like to talk to some other applications, and this part and finally that part. So what happens here? Okay? That is the plan. Okay, so I was going to tell you about some motivation, but maybe I want to continue. You know, we care about these deformations, Q-Gorenstein deformations, because they are the ones, these are the deformations that appear in this compactification by Kolar-Sheffer-Barron. So that is one motivation. So you have a degeneration of a smooth projective surface or smooth projective surfaces into this boundary so that you have only log terminal singularities or quotient singularities, then this situation appears. But then the canonical class, so when you are in this moduli space, the canonical class is ample. Now I would like to get rid of that and put a general situation, like in here. Maybe it's not even Neff, then what do I do? And also, if you have any degeneration, well, at the end I'm talking about that, you can reduce this degeneration to a minimal model where you have simple normal crossing singularities in the central fiber, or Wahl singularities, or these orbifold normal crossing singularities. So kind of, you see, there is a sort of canonical way to replace any degeneration to a degeneration, for example, with only Wahl singularities. But I will not be talking about these other ones that also appear. Okay, so this is the definition. So sorry about presenting this with slides, but I think that I will not have enough time, but I will try to go slow with the slides. And please ask questions. So I have this situation. So now this is systematic. Now I have the deformation, the same. So this is a Q-Gorenstein smoothing. But okay, let me see. Let me say that I will call this situation a W surface, which is a normal projective surface, W, that has only Wahl singularities. This is going to be the central fiber, inside of a threefold that is fiber over D. So it's exactly the same, but this is a proper deformation. So now I have only these proper surfaces. The W has canonical class, which is Q Cartier. The central fiber is W, and WT is non-singular. Okay? So this is my object. And we say that this W surface is smooth if W actually is not singular. So a smooth deformation. Fact about this situation is that the irregularity for all fibers is the same. It's constant. It doesn't jump. The geometric genus is also constant. K squared is constant. So if you get the singular surface and K squared is 8, then it's 8 for all the fibers. The Euler characteristic, the topological, is constant. So all of these numbers are constant in these deformations. The fundamental group might be different. So for example, yesterday I showed you an example of a degeneration of an Enriquez surface, where you have in the central fiber a rational surface, where the fundamental group is trivial, but the Enriquez has fundamental group Z2. Okay, so it's not necessarily constant. And then you can prove that if canonical class of W, if the canonical class of W, which means the central fiber is Neff, then it's Neff for all the fibers. And if it's ample, then it's ample for all the fibers. And in that case, you can think about this degeneration as a KSVA limit. So you are in the moduli space going to the boundary. Okay? So this is the definition. Now I want to explain this. So this is the starting point of the birational geometry. So there is an MMP on these degenerations, which is relative to D, and for the canonical class of the threefold. But everything will be read from the surface, okay, from W. So this is the situation. If canonical class of W is not Neff, so if it's Neff, then we call it a minimal model of the deformation of the W surface. If it's Neff, if it's not Neff, then we have this again, this gamma minus, which is again a P1, C, inside of the W, which is inside of this deformation over a disk. and this is over a distinguished point that I denoted by 0. And then you do the following. So, and so what is the meaning that this curve exists is, so this is not f, so kw dot gamma minus is negative. And say at the beginning, so I want to explain this blue part. So at the beginning that the self-intersection of this curve is negative. Remember that now we are on a singular surface, so this is a negative rational number in general. So n gamma minus square is negative. So then what you do is you have the w, and there is a contraction of this negative curve, and that goes to this y. So this is a contraction. This is inside of a w. And then we have, in this situation, an implication that the deformation blows down also. And this is going to be inside of another threefold. So now you have a birational, and this is going to be birational map between two threefolds. This is what we call, well, this is going to be this extremal neighborhood corresponding to this curve. Yeah, this is from W to Y. Here I have a deformation, but it turns out that you can blow down this deformation, so you have a diagram like this. This is over a disk, and now this is over a disk. So, yeah, so you have a deformation of, so there is a family, so this Y is a central fiber for that family. This is always, all of them are over this distinguished point. And then there is a birational map between the fibers. So I have a situation like this. And now, so I would like to see what happens here, and the things are going to split into two operations, so it's going to be a bit more difficult. One of them is divisorial contraction. And for a divisorial contraction, I will have that this curve lift to the general fiber, and you will see a divisor that contracts to this other threefold. And I will explain what really happens, but this will be the generalization of Castelnuovo. But there is also this flip, which is new. It didn't appear in the two-dimensional classical case. And I will talk about that. So today I will explain these birational operations, these two, at the beginning, and their families. There are families of these situations. So whenever you have a situation like this, negative situation, you will have not only one situation like this, and where you have a blow down of a -1 curve, but you have a family of situations. And that family is expressed combinatorially in what I call Mori trains. You will see Mori trains. It is possible, yeah. So yes, this is a case that I will not mention, but if this gamma minus doesn't pass through any singularity here, then it must be a -1 curve, and this -1 curve will lift to the general fiber, and then you have like a Castelnuovo, but in a family. There is a contraction. But when you pass through one singularity, then something else happens. I will explain that. Was that the question? Okay. What is ruled out? Okay. So everything that I do is happening really. So everything that I do will happen on this W. So on W, I can check if the canonical class is NEF or not. On W, I will have this curve that is negative with respect to canonical class, and so on. So everything can be read from W. That is what I meant. Okay, so let me show you one example before going to the general picture. So I told you that examples look like this. Here you have, oh, can you see the example? Maybe can we make it bigger? I don't care about this black part. But not that much. Okay, but later we go down. No, now up. Thank you. So there you have this is an example of a flip. So here you have an elliptic vibration, which is coming from a pencil of cubics in P2, and you have exactly these 4 singular fibers, and you have these 3 sections, and this is the configuration. Now you have these blow-ups that are shown here, and you will see several wall chains that are denoted here. You can see them here if you don't see them on the picture. Okay? This appeared in this paper of Park, and Chin about complex surfaces with k²3 that are simply connected and PG0. But these complex surfaces, I mean non-singular. They were trying to construct them using this procedure, and where you find this W, prove that there is no obstruction, and then you have a smoothing, and you construct the surface. But to say that this surface is going to be of general type, they needed to say that the canonical class on the central fiber is Neff, at least. Well, if you prove that it's Neff and k² is bigger than 0, then it's Neff and big, and you have something of general type on the general fiber. But so they constructed one example, they proved everything, that example is okay, but then they say there are more. They show this, but here there is some error. And this error helps me to tell you about the flips. So if you look at this picture, there is this -1 curve between 2 chains. You see it there in orange. And so this is a zoom of that particular situation where you have the 2, 5. You see the 2, 5, and then you have the 3, 5, and so on the other side. And this -1 is in between here. If you do the computation of discrepancies, you get this discrepancy and that discrepancy for the exceptional curves that are intersecting this curve, this P1 with self-intersection -1, and so you compute in this way, and then this is negative. So, oops, the canonical class is not Neff. And they realized, and they wrote here how you call this, under Ratum, but in the Ratum they put another example where the canonical class was Neff. But the thing is that there is this operation of flip where you take this and you replace it by the flip, which is this. And so what you do, more or less, you take this, which is a -1 curve, you contract everything until you cannot continue contracting -1 curves. Then you have a cyclic quotient singularity, which will be below this. Like you put here an arrow, you have a cyclic quotient singularity. And over this cyclic quotient singularity, you want to see a P resolution. So a situation like this, but where the curve in between is positive with respect to canonical class. And that is the one. You do that, can you go down now? And it turns out that the example is fixed. And now you have this situation. So above, this curve was around here. And now it moved to this place. And here you can compute that the canonical class is Neff. So the example is actually okay. And this is an example of a flip. Now we go to so what we did in the same example was this. There was a negative curve with respect to canonical class, like this. There you have the singularities. And now we have this birational map, which is called flip, but it's over the cyclic quotient singularity that you can compute, is that one, over this surface. And so this surface that I put with a negative has the negative curve, and the positive has this positive curve that you do the flip. And now, you have a question? No.
Singularities on W, capital W plus?
Yeah, those are terminal singularities which we can write down. Yeah, but we don't really need them to do this. And then you have this situation. Okay? So now I wanted to tell you a bit about the Mori train behind this. So you have this negative situation, right? Well, it turns out, and you have this positive. It turns out that this negative situation is connected to a family of negative situations. And so this particular situation is here. So you have the phi 2, this dash is the -1 curve, and then you have this other singularity. But it turns out that you can change it to this other situation where you have this singularity and this other singularity and also a -1 curve in between here, and this keeps going forever. And that is going to be the Mori train. This is the picture. I will explain you what is going on. Okay? And what is important about this Mori train is that there is a particular number, which is my delta here, which is essentially the intersection that you have with the canonical class, in here, the negative part or the positive part, but times the indices of the singularity. And there you see this 3, which is -3 because it's negative here. Or, well, if you do it in the other side, you will have a +3 over these 2 indices. Okay, this is our delta. So delta related to intersection with canonical class. Okay? Okay, so now I go to the general picture. So in general, an extremal neighborhood will be a situation where you have a curve inside of a threefold, and there is this birational proper map to a y, which is a threefold too, and you are contracting this curve to P, so that the canonical class is Q-Cartier. W minus has only terminal singularities. The preimage of this point is the irreducible curve gamma minus, and you have that the intersection is negative. This is what is called an extremal neighborhood. And from there, you will have this MMP. So you need to analyze when I have a flip, when I have a divisorial contraction, what are the possible situations. And Kolar-Mori or Mori divide this extremal neighborhood in semi-stable. Semi-stable are related to our case, where you have a degeneration, or exceptional, which is the other case. And these exceptional are classified, so this is a parenthesis in the paper that has, it's like a book, 170 pages. In the appendix of this paper by Kolar and Mori and Jams, 92, you have the classification of the exceptional. Now I will not show you all the semi-stable situations. Some of them appear in our picture, okay? But are divided in semi-stable and exceptional. A good source where you can read this like in 2 pages to have an idea, and very much related to what I'm going to do, is this paper by Mori on 2002, which is called On Semi-Stable Extremal Neighborhood, where you have a classification for the K2A case. Okay? In case you want to see how this picture appears, he talks about that, give you references, so on. Okay. So the only extremal neighborhood that we will see are the type K1A and K2A, which are minimal in the sense that, so you have this irreducible curve, and the singularities are the minimal possible, and that means Wahl singularities. Okay, only two or one Wahl singularity and an irreducible curve. And each of these extremal neighborhoods, so you have a W and a Y, and there was a point here. This point is always a cyclic quotient singularity, which now I will denote by 1 over delta, 1 omega. And this family, the family of the Mori train, is going to be over this singularity. And the flip, when we have a flip, is over this singularity, okay? So you will have 3 invariants, this delta, this omega, and the other delta. Not the capital one, but the other one, which I forgot now how to call it. Okay, so now I will describe you the K1A, okay? So for the K1A, 1 or 2 means 1 singularity or 2 singularities, okay? K1A, 1 singularity, K2A, 2 singularities. So you have a negative curve like this. This is my gamma minus, like in the board there. And you have a Wahl singularity where this curve is passing. And then there is a contraction to this cyclic quotient singularity. So this is the situation on surfaces for the K1A. Now, you want to know exactly what is this gamma minus. So here I minimally resolve, and I am showing you what happens. You have the minimal resolution of the Wahl singularity, and the gamma minus is touching some EI at one point, and it's a -1 curve. And again, you contract this -1, maybe the EI was a -2, so now it becomes a -1. You keep going until you reach the cyclic quotient singularity. And that is the contraction, okay? And now some numbers, you can compute easily the intersection with gamma minus, which is going to be minus delta over n, sorry. And gamma minus square is exactly this number. So here you have the big delta of the cyclic quotient singularity over the index square, okay? Just formulas. I wanted to show you formulas. And now, oh, maybe you don't see completely here. Well, delta is computed like this. You compute discrepancy plus 1 and multiply by n. This is my little delta. And now the symbol for the K1A will be this one. I don't know if you see it, but it's just the Wahl chain. And I specify where you put the -1 curve. This is going to be the symbol in the Mori train, so that you remember where to put the -1. This is K1A. K2A is similar. Now you have two singularities. So there are two Wahl singularities and this negative curve that you contract and you go to a cyclic quotient singularity. If you resolve, so you have a situation like this, where there is this -1 curve in between these two resolutions, but this -1 curve is touching the ends of the resolution. So you have a chain. And then you contract this chain, and you go to the cyclic quotient singularity, and you have these numbers.
Is that the example of arc that you showed us?
In the flip, yeah, I think that we have this situation. Let me see. Yeah, we have exactly that situation. Where you have, this is a K2A, where you have two Wahl chains and the -1 in between. And this -1 is negative for the canonical class. And that's it. These are the two situations. These are the two extremal neighborhoods. Okay, so now you are wondering, well, I have the extremal neighborhood, so how do I know if I have a flip or a divisorial contraction? And how to perform these things. So first, I will explain how to check there is a flip or divisorial contraction. And this is due to Mori for the case of K2A in this paper that I mentioned. You can find it there. So there is a Mori algorithm. So let me explain it in this way. Here, say that you are starting here. Okay, you have a K2A, so you have two singularities in this negative curve with respect to canonical class. Now say that I organize this so that the N0 is bigger than N1, because I want to know where to stop. And then it turns out that you move from this neighborhood to this other neighborhood, and where you copy this Wahl singularity up here, and then you transform the other into this one. And you see the index is exactly delta, this little delta, times N1 minus N0. And then you compute the corresponding A of the Wahl singularity in the same way. Or you can take it to the left, and where you change this N1 A1 by that, which is exactly the same formula, and you keep the N0 A0 here. And this is going to be negative, and you will have an extremal neighborhood of the same kind, K2A. This is also negative. And you keep going. So if delta is bigger than 2, 1 is a particular example where you stop in both directions. But if it's bigger than 1, so for example 2, you go forever to the left in this thing, and that is why we have this Mori train. And then on the right, you will stop. At some point, this operation will be negative or 0. Theorem of Mori, if it's 0, you have a divisorial contraction. If it's negative, you have a flip. Okay? That is the way you realize when you have one or the other. Now, let me say that behind the scene here, you have this negative continuous fraction, which is infinite, and so you have this quadratic number behind. in the algorithm. So the limit of the ni over ni plus 1 is, when I goes to infinity, is this number. So there is a quadratic irrational number behind this. Okay, so now I want to talk about this family of negative situations, and this is in our paper with Genia and Paul Hacking, 2017. So there is a universal family of extremal neighborhoods for flips or divisorial contractions, and I would like to explain it like this. So you imagine a chain of P1s, infinite chain. When they intersect, over that, you have the K2As that I was explaining with the Mori algorithm. But on the general point of the P1, you have this K1A. But this is not a random one. You see that on the extremes, the K2A, you have the same singularity. So when you go to the inside of this P1, you are smoothing the singularity on the top or the singularity on the bottom here. And you keep the other one. So it's like the other one is traveling. So you have two singularities, the other one travels along, and then finds another couple. And then you keep going like this. And so you have this universal family. And this is over the same, and this is going to be over the same cyclic quotient singularity, and that means when you contract any of these, you go to this singularity, and the same delta. Okay? So this is our universal family. And now let me explain you the situation of divisorial type, what is going on. So say that in the algorithm, we get into this 0, which, so you remember, the theorem of Mori says that you run this and you want to know if it's 0 or negative. This is the case of 0. And then we will have a divisorial contraction. So here is the negative curve that you contract to some cyclic quotient singularity, but in the case of divisorial contraction, this has to be a Wahl singularity. And this smoothing in here has to be Q Cartier. So you go from a W surface to another W surface. Okay? And on the general fiber, which is smooth, you will see a lifting of this curve, which is a -1 curve. So on the general fiber, you will see a Castelnuovo blowdown. So you have this divisor, you have -1 curves that degenerate to this gamma minus that is passing through one singularity or two singularities. There I draw one dot, but could be two, okay? And then you contract. And it happens, so when you have one Wahl singularity, I can give you what is the Mori train. I can write it down explicitly. And the meaning of the Mori train is, as I said, this dot here is my -1 curve, and then you have these two singularities. One of them is exactly the Wahl singularity you started with, and the other one is this one, and you keep going. So we understand pretty well, and we have this family. Okay? So I don't know if you can see it, that you have this curve, and you can move it to acquire another Wahl singularity, and then eliminate the other, and keep going forever, and they are all by divisorial contractions that you can contract to this situation. Here you have an example. If you have the minimal possible Wahl singularity, which is a quarter 1-1, that you resolve with a -4 curve, then this is the Mori train, precisely. And you can check if here there is a -1 curve. So this would be a K1A. You contract a -1 and keep contracting, and you will get 4. So here you are over 4, over 4, over 4, and so on. And this is the train. For a flip, it's a bit more complicated, but not too much. You have this negative curve, which is also over a cyclic quotient singularity, and this is not a Wahl singularity anymore. Oh, it could be a Wahl singularity, but the smoothing is not Q-Gorenstein. It could be a Wahl singularity, but typically it's not. And then to do the flip, you need a partial resolution where you have a positive curve. You have these two Wahl singularities, positive curve with respect to canonical class. And then there is a Q-Gorenstein smoothing. And that is going to be the flip. And this situation on the level of surfaces, so over the cyclic quotient singularity, you have this, is a p-resolution. I was telling you about p-resolutions, but these are extremal p-resolutions in the sense that you have the minimal possible amount of curves over this cyclic quotient singularity, and you have only two Wahl singularities, which are the smallest ones. So that is the meaning of extremal, minimal, if you want. Yes?
But in this particular case, gamma minus 1 is positive on the canonical class of capital W. Am I right?
Where? Sorry.
In that particular diagram.
Here,
Gamma minus, exactly. Gamma minus.
this is negative with respect to canonical class. This is the negative situation. That is why I put a minus here. Negative with respect to canonical class, and I move to positive with respect to canonical class. Okay?
The canonical class of capital W.
Of, yeah, canonical class of this surface, capital W minus.
Oh, I meant the other one.
Yeah, but it's going to be the same. Actually, it's the same. Yeah. Yeah, the other day I said that sometimes when you have a cyclic quotient singularity and you wonder what is the p-resolution that you need to put here, you have two options. But in the algorithm, you know what the option is. So we know how to do it. In practice, typically, you have only one, and you will see it. Okay, and well, you have these numbers, but maybe I will not focus on that. But maybe the important part is when you do the flip, you see you have Wahl and Wahl. This is a Q-Gorenstein smoothing, so we are a W surface again. So we stay as a W surface, always, okay? Okay, so the singularity, the cyclic quotient singularity, might be Wahl singularity, but in that case, the canonical class cannot be Q-Cartier again. So you need to find this p-resolution. Yeah, as you were asking about this, the cyclic quotient singularity might have at most two extremal p-resolutions. I told you about that in the first class of the mini course. But you know exactly which one it is. Here I have an example of a flip so in this example, this is the cyclic quotient singularity. So 11, and then you have 3 as omega. And then you have this p-resolution, which is extremal. So you know 11 over 3, it's not difficult. 11 over 3 is 4 minus 1 over 3. So you resolve with a minus 4 and a minus 3. So this is minimal resolution, minus 4, minus 3. So for the extremal p-resolution, I will have this curve, and I contract the minus 4. So you have here the Wahl singularity. And this is my situation over the cyclic quotient singularity. So that is the positive side. But for this positive side, if you want to, so for this positive side, you have two options. You will have two Mori trains of negative extremal neighborhoods. If you want to keep this singularity, then you have one train, and if you want to keep that singularity, which is not singularity, it's a smooth point, and that could happen in the positive part, then you have this other situation. So if you compute, you have this Mori train and that Mori train over that p-resolution. So you have a p-resolution, and typically there are two Mori trains of negative neighborhoods that all go to this positive unique situation, okay? This is an example of a usual flip, so a flip that you see easy to compute. So let me show you here this example, and then you will understand. So you have a surface, and where there is a curve, which is negative with respect to canonical class, and this Wahl singularity. I mean, you can prove that this curve, if it's touching only this minus 2, then the intersection is negative. What I mean, you have this situation, minus 1, and this is the minus 2 there, and you end with a minus 3. Okay, so you contract. This is the resolution of W minus. So you contract to W that has this Wahl singularity corresponding to this chain, and there is a gamma minus. okay? And gamma minus dot k, W is negative. We have that situation. I say, so this proposition tells you that in a situation like this, where you put a -1 curve on the end of this wall chain, could be this end or the other end, doesn't matter, and you have a situation like this, then, and say that here you have so this is inside, this is the gamma minus, inside of a threefold, then this situation is always flip. It's always flip, and the flip goes like this. So you contract the -1, this becomes -1, -1, -1, and you reach this curve, which is going to be -6. So you have 6, 2, 2. This is wall. And then this is free now. And so you have 6, 2, 2, and you partially resolve the last curve. And this is the P resolution. So again, you take the negative curve is on an extreme. You keep going. You get a wall singularity always. And the other end is the positive curve. And this is flip. And this is the P resolution. This is another example. This is -1, -2 becomes -1, and this becomes -4. And then you keep 4 and freedom for 3. Okay? That is the way it works. I wanted to show you one flip that you can compute easily. And you see that. So tomorrow I think that I will show you how this, when you run this, how the picture is. And you will see a lot of these kind of usual flips. So this is summary. You have a W surface. Now we can run MMP, staying on the world of W surfaces. You never go outside of this. And then using only this K1A that I explained and K2A extremal neighborhoods. MMP terminates, this is an observation, because explicitly at each birational operation, two things might happen. One is that one of the indices of the singularities, so you have many singularities, one of the indices has to decrease strictly, and the other stays the same or decrease. So if you do a flip, one of the singularities get better, the index goes down. So if you cannot keep doing this forever, or when you have a divisorial contraction, the Picard number decreases. So if that happens, then it has to end, okay? That is why it terminates. So now in this last part, so this was about, so that is the replacement of this part here. That is what you do. So you replace this flow down of a -1 curve by that. Yeah. So now I want to talk about this yellow part. So what are the actual minimal models that you can get when W is singular, okay? When W is singular. If it's smooth, of course, then you have the whole thing here for using as a central fiber, this guy. But when it's singular, I would like to know what do I get as a W. Okay, so to finish for today, I will explore this, and I will give you some other open questions. There are open questions here. So say that I have the situation, this deformation, but now the canonical class is Neff and singular, okay? So the canonical class is Neff and W is singular. There are some singularities. So is there any classification of W, which is the central fiber? Is there any classification of WT, which is the general one? So say that we have that situation I just told you. Then let us explore what happens with WT. So you know the canonical class is Neff. So in the general fiber, you have canonical class Neff. So you have codaric dimension 0, 1, or 2. When it is 0 and W is singular, I would like to emphasize that because you might take, for example, a K3 surface, a configuration of curves, which I do blow-ups, contract, and then I have a situation like this. But if you run MMP, then you will get a smooth deformation of a K3. So it will not be in this list, it turns out. The only thing that can happen when you have W singular and KW Neff is that the general fiber is an Enrique surface for the codaric dimension 0. And actually, the singularities have to be quarter-1-1 singularities and no other. And if you are interested on that situation, actually I wrote a paper about that, which is called Cabo, Mukai, lattice, and so on. Okay, there I describe a little bit of that situation. Then codalized dimension 1, Kawamata actually has a paper. So what is this? Kawamata has a paper that classifies this situation. So what you have is that the W is actually an elliptic fibration, the W, the singular one, but on the singular fibers, you find these Wahl singularities. So there is an elliptic fibration, but with singularities. And that goes to an elliptic fibration on the general fiber. And he classifies that in a paper that is called Moderate Degenerations of Surfaces and Applications, something like that. Very nice paper. There is a lot there. And I show you on Tuesday examples of that. You remember Enriquez and Dolgachev 2-3 surfaces? Well, Enriquez is in the other case, but Dolgachev 2-3 is here, where you have the situation where there is a multiple fiber that collapses with an I1 fiber, and then you have an I1, which is multiple, but there is a singularity on the node. That kind of thing is what happens in this case. So we know very much Kodaira 0, Kodaira 1, and Kodaira 2 is super hard. It's kind of difficult to classify. But in all cases, the irregularity is 0. Yes?
So can you recall us what assumptions you put on Wahl surface? Is just Wahl singularities?
Just Wahl singularities? No, Wahl singularities and anything. So a situation, a W surface that is minimal. I'm trying to see what are the possibilities for WT. And W has Wahl singularities and canonical class Neff. Hmm? Yes, for all of them. Yeah. If it's singular. If it's singular, the W. Because as I said, well, I can construct artificially a situation where Q is not 0. But then if you run MMP, then it is a smooth deformation. So if it's singular, then this happens. It's only for irregularity 0 surfaces. So there is no Albanese map. Albanese map is trivial. Okay, so what about W? W, the singular one. So for W, you have that it could be rational. So this would be Kodaira. So when you resolve Kodaira dimension minus infinity, could be rational. And that is the hardest case. That is the most difficult case to classify when, for example, you want to know what are the possible degenerations for surfaces of general type with certain invariants. Then the hardest case is always rational. And I will tell you why. Those are the open questions. And then if it's not rational, so rational means the case of root surfaces. If it's not rational, then S could be a K3 or Enriquez. So think in this way. This is a K3 or Enriquez. Then there is a configuration of rational curves. There are blow-ups. You go here to X. Then here you have the Wahl chains that you contract to W. And now W, oh, I forgot to say that here I'm thinking about KW Neff and big. Neff and big, so the case of general type, when you have the general fiber would be, the smooth fibers are of general type, okay? Neff and big. Then you start with a K3 or Enriquez. We can also start with an elliptic fibration, but it's going to be over P1 because Q is 0. And then S could be of general type, and irregularity is 0, and you have this situation. You know that S is so I forgot maybe to tell that. W is the one that is singular, X is the minimal resolution. And now I go to this S, which is the minimal model of that X. So there are no -1 curves in S. And when you go to that minimal model, you compute K squared has to be strictly smaller than KW squared. Okay? That is what we know in general. And now let me tell you about some open questions. Okay, some open problems. I will tell you about 2 open problems. So say that we want to describe the situation for W's with only wall singularities when you fix k squared. So when you fix k squared, say that you are thinking about the modular space of surfaces of general type for k squared equal to 7. Okay? And you want to see what are the possible degenerations to the boundary with these wall singularities. Well, by Alexiv, we know that this is a bounded situation, so there is a finite list of these singularities. Remember that here k is big and F, so it's positive. If you don't put that requirement, Mori trains give you infinitely many. Okay? So you need to put this positive requirement. And then there is a theorem by Alexiv that this list is finite. So the question is it possible to write down an explicit bound on the length of these wall singularities? So I fix k squared, say 7. I would like to know what is the maximum length. Because if there is a finite list, there is a maximum one. Well, the answer is yes, when W is not rational. You can do that. Now, you have a bound on the length, but then you need to check if that actually happens. So you have a list, but it's not guaranteed that this list appears in your modular space. Then you need to check what really happens. So I wrote a paper with Julie Rana in 2019 when you have only one singularity in W. So for only one singularity, and then the length of the wall chain is this R, and is bounded by 4 times k squared plus 1. And we are more optimal, and we are optimal. We go case by case, checking what happens for different codiral dimensions, and also what happens when you have equality. We classify the whole situation. And then with Fernando Figueroa and Julie Rana, we did arbitrarily many wall singularities. Actually, T singularities, right? Let us say wall singularities. And then, I want to explain this like this. If there are no weirdo exceptionals on this situation, let me show you. So, when you prove this kind of thing, you need to play between the exceptional curves from X to W, the wall chains, and the exceptional curves from S to X. So say this is C and this is E, and you want to see how they interact. Now there are some weirdo E's that make you the life difficult. Those are the weirdo ones that I don't want to explain. So if there are no those, if you don't have those, then you can put this explicit optimal inequality. So the sum of the length of the wall singularities is bounded by this. Now there is a way to bound the number of wall singularities. Then here you have k squared. This is negative. And if canonical class is Nef, so we are not rational, if canonical class is Nef, this is a bound. But also in that paper, we classify weirdo exceptional. And so if you have a particular situation, you say, well, I have either this or I have this finite list. It's like a codiral table of configurations that are bad. And then you look at, and then you try to find these configurations in your situation. Maybe you can say, no, this doesn't happen, that doesn't happen, so we have this. Okay? We also put a general bound, right? But I like to present it in this way. But the big challenge is to find any explicit bound when W is rational. And really, I like to put it like this. Give me any. I would like to see one. Okay? And then we try to make it optimal, but give me any. I think that is kind of big challenge to find one. Any questions about the open first problem? I was actually pushing Alexiv about this bound, and we couldn't figure it out. I can tell you.
Do you know about if there are no weird exceptionals?
Hmm?
Do you know about if there are no weird exceptionals?
No, I don't know any bound. I can tell you, for example, in the paper with Julie, we actually analyze what happens when it's rational, but then you have a bound that depends on this number. For example, say that S is P2. So we have this number, but then canonical class is negative, so you have the degree of the curve here. And so with the degree of the curve, by using Cremona transformation, you can make it arbitrarily large. So it's really a question about how to find the minimal degree for this image of the exceptional device. It's about that, this question. For me, it's very impressive, this boundedness of Alexip when you work with rational surfaces. You don't believe that is happening, but it happens. Okay, so the other open problem, say that now we fix k squared of W, and for now, forget about smoothing W. Say that we have a W with Wahl singularities and canonical class big and F. I fix k squared, and I would like to classify all of them. Now, we have to be careful because we saw a lot of possibilities when PG is 0 or 1. I told you that when PG is 0 and k squared, for example, is 3, then the number of possibilities is like 2,000, at least. So how to do how to do that classification? I can repeat. But say that at least we would like to do it for low k squared. So you know that k squared goes from the nether line, where you have the Horikawa surfaces, to the Bogomolov-Miyaoka-Yao line, where you have these ball quotients. And you go from easier to handle to very difficult. Now, say that we want to work with the simplest that were actually classified by Horikawa. So k squared equals 2pg minus 4. Or even the next case, or low k squared, 2pg minus 3, where with 2pg minus 3, you have quintics, for example, or these I surfaces. Is it possible to classify that situation? So I said that I don't care about smoothings. So there is one question. Classify the W, and then check if these W's are smoothable. Because in this Kolar-Sheffer-Barron compactification, you have also weirdness. You have these weirdo components that parameterize surfaces that are always singular. So it's not like MG, where you have that the closure is this boundary and you have something irreducible. You might have components with singular surfaces. So it's really a question, do I have a smoothing of the W? Okay? And it turns out that we can classify them. So we have a classification of all Horikawa surfaces with only Wahl singularities. And I did that with my students Vicente Monreal and Jaime Negrete. This year we finished. It was a long project, like 2 years. And it turns out that they are either Lee Park examples, which are particular examples, the only ones that we knew, the only ones that you can check in the literature, and a big list that we classify of small surfaces. Instead of defining small surfaces, I will show you examples in a moment. And why we did this? This was done because of this famous Horikawa problem. So our motivation was not to find really a classification for the first case of surfaces of the general type, but we have in mind this famous Horikawa problem. I will talk about that in 2 more weeks. And as byproducts of the methods that we found to work with this, we can classify also the case of 2pg minus 3, where you have I surfaces and quintics. So we have complete list of everything that can happen. It's not partial, complete. And here you have more than small surfaces. The combinatorics is a bit more difficult, but this is not going to be in the coming up paper about that. And then, I am good on time, and maybe we will have some questions, because the next one is the last slide. I will show you the smallest possible Horikawa situation, which is k squared equal to 2. So, okay, let me explain this picture. So this is a complete example, k squared equals to 2, so PG is 3. We have these Horikawa surfaces that are double covers of P2 branch along optics. And so the question, so I did this work with Johnny Evans, Angelica Simonetti this year. And the question was, where are the degenerations? What are the degenerations? Here you have the moduli space of these Horikawa surfaces. What are these W surfaces that we can have from this moduli space? And it turns out that we were able to classify these completely. And you have two types. One type is that one. This is the Lee Park situation, and where you have an elliptic fibration over P1, where these 2 minus 4 curves are sections. So that is something that everyone knew. But then you have this other situation where you have a more complicated, you have a section, and then there is this singular fiber and an extra minus 2. This is in this paper, which is in the archive. And we describe that. What we use as a tool is the following. When you have, well, there you see, if you have a Horikawa surface in this situation, then there is a double cover of P2. So if you have a degeneration, a W surface, then you can use the involution and see a degeneration of P2 into a surface. And it turns out that surface has to have quotient singularities, and that is classified. That will be tomorrow. That is classified, and there you will see these Markov numbers, this Markov equation and everything. And then, using that, we can reconstruct, we can see, we can check what is possible and what is not possible. The key is to go down, to use the involution and see this on the level of degenerations of P2. Okay, but then I told you, let us say that we don't care about smoothings. Is it true that the only W surfaces with Wahl singularities are these ones? And the answer is no. You have two more families, and there you have the other two. Now, here you have the definition of small. Small means that on the configuration, they are always elliptic fibrations. And on the configuration, you have only one section, and then either complete fibers of the elliptic fibration or partial part of the fiber. But the point is to have only one section. That is the definition of a small surface. And what we do in the paper I mentioned with my students is that we classify all small surfaces for any situation, not only Horikawa. And in this case, you can prove that these are the three possibilities for small surfaces. And you know a corollary of what we did with Evans and Simonetti is that these two are not smoothable. And that is also a typical situation that we can see. You classify all W's with this property that the canonical class is big and F, only Wahl singularities, and typically these small surfaces do not smooth. But sometimes they do, like this one.
By that you mean will not fit in a family?
Will not fit in a family where the general fiber is a Horikawa surface. Yeah. Actually, when you classify these small surfaces, you realize that you can go beyond the Horikawa bound, beyond the nether line. So you can go down. And of course, if you go down, it's impossible to smooth. And so we actually classify what happens between half the nether line and the nether line, complete classification of that. And there you can see only, using algebraic geometry, only these small surfaces. And well, whatever. So that is coming up. It's not in the archive, but will be soon. So maybe we have 15 minutes for questions. This is the end.